Is our final lecture, actually. So let us get going here and see where we get to. So we were talking about carbohydrates. Carbohydrates obviously are also referred to as sugars, and they basically contain carbon, hydrogen, and oxygen. And we talked about a couple of different types of sort of sugars. We can have some that will have a aldehyde group up on top, and those were referred to as an aldose because of this aldehyde group. Obviously, some OHs and stuff like that. For example, an OH over here. At the last chirocarbon, as we talked about, chirocarbon being, a carbon that basically has 4 different groups attached. This OH is on the right, so this would be the D anomer. We also saw some carbohydrates that actually have a ketone group basically on it. Just kind of draw this type of deal. And again, obviously there would be more OHs. I'll just draw the guy on the bottom. If this was our last chirocarbon here, OH is on the left, that would be the L. This is what is referred to as a ketose. Again, basically has your ketone group right there. We also talked about ways to classify these guys by the number of carbons. Like pentose has obviously 5, hexose has 6, tetrose has 4, and so forth. These are sometimes referred to as monosaccharides, and monosaccharides can also sort of, form themselves into a cyclic structure or ring type structure, which is, I think, is where we sort of finished up on last time, how to kind of put these guys into a ring type structure. So, if you have a guy like this, remember, sort of the goal here is first off, you want to figure out how many carbons you got. So that would be carbon 1, that would be carbon 2, that would be carbon 3, carbon 4, carbon 5, and carbon 6. So this is a hexose, which means usually it's carbon number 5 here that's going to go and find that carbon oxygen double bond, and that gets you 1, 2, 3, 4, 5 carbons. And remember, there's pretty much 2 types of rings you could draw. One is kind of like cyclohexane, again, except it has a circle. No, it's got an oxygen in it, which basically is 5 carbons. And there's also one that kind of looks like cyclopentane that also, again, has 4 carbons because it has the oxygen inserted. So here we would draw the sort of 5-member ring here. And remember that we do see that this carbon number 6 is typically not part of the ring, always ends up to the left there of that oxygen. And then we could go backwards in terms of our numbering: 6, 5, 4, 3, 2, 1. And remember, I ran out of room here, but typically what we do is we kind of drop this guy on its side. And basically when you drop the guy on the side, everybody that's on the right-hand side basically ends up down. And everybody on the left-hand side basically ends up up. And we don't do number 5 because that's, again, where the ring kind of closes in on each other. So we do skip it and go number 4. And number 4, we see the OH is on the right, which means it would come down. Number 3, we see the OH is on the left, which means it would come up. And number 2 there, we see the OH is on the right, which means it should come down. Remember, the last one is either alpha or beta, and usually they will tell you sort of which one to draw. Alpha means that the OH group is going to end up down. Beta would mean the OH group would end up up. So why don't we just do beta here, and that would be the beta anomer for this guy. We also talked about kind of breaking it back up from the ring, going back this way. And again, based on what you see, if you see a carbon that's sort of off of the ring, that typically would indicate this type of ring that you would need. or it has basically that many carbons in the ring part. If not, then obviously it's most likely going to be an aldehyde group rather than a ketone group. Any questions on that stuff? I think we talked about there last time. Okay, then let us continue here. So again, this is sort of the summary, and just to let you know again how the oxygen sort of gets incorporated into the ring here. This oxygen here basically comes in and closes up the ring, and that's actually the OH group there at carbon number 5. And the hydrogen kind of makes its way over to here, and that becomes a single bond, and the OH group ends up over here. And that's again carbon number 5's oxygen that gets incorporated there. The double bond actually becomes the OH group that's on the outside here at carbon number 1 in this particular case. And again, we make a new chirocarbon, which has one group that's different, two groups is different. You know, everything to the left here is different, and everything to the right there is different as well. Now, glucose, alpha D-glucose and beta D-glucose, they kind of will open up and kind of close the ring. And we see that for a majority of the situation, it pretty much will be in that beta form over here, 64% of the time. Again, the beta, because here again is carbon number 1, OH group is up. This is again our alpha OH group at carbon number 1, again going backwards, 6, 5, 4, 3, 2, and 1. We have it down. As you can see, for a little bit of amount, you know, it's in the open sort of process, usually sort of as it's going back and forth is kind of where you get that trace amounts of it. So mainly what we do see is sort of beta D-glucose being formed. Now, when we look at something like fructose, which is also 6 carbons, but it is that keto, which is that ketone group. Because of that, as we talked about, I think the other day as well, but just to reiterate, if we sort of counted here, this would be carbon 1, 2, 3, 4, 5, and 6. Again, in the 6 sort of structure where there's 6 carbons, it is going to be that 5th carbon. Remember, it's not going to always go to carbon number 1. What it is really looking for is this guy, the carbonyl carbon. So it's going to go find that carbon there to close up the ring. And because it does that, as we could kind of see here in the picture, we actually only end up with 1, 2, 3, 4 carbons as part of the ring. Hence, we do our 4-member ring here. The consequence of sort of how that closes up is, in addition to our normal carbon number 6, which ends up off of the ring, we also see, I'm sorry, carbon number 6 down here ends up off the ring. We also see carbon number 1, we'll highlight it the same color, ends up off of the ring as well. So again, if we were counting sort of the carbons over here, this would be carbon 6, this would be 5, this would be 4, this would be 3, this would be 2, and now carbon 1 is actually here. Again, we could have our alpha, which would put carbon 1 upwards, and we could have our beta, which would obviously put our carbon number 1 down in that sense. So that's what I was talking about just a second ago. If you sort of have the ring structure like this, and you see a couple of carbon groups that are off of the ring, that's sort of how you could deduce that you probably got that ketose group or ketone group happening in your carbohydrate, as opposed to when we looked at, say, glucose there on the last slide, really only have 1 carbon group, which is carbon number 6, no other carbon hanging off on the other side. And that's how you could kind of deduce it probably came from the aldose or aldehyde group on top of the carbohydrate. So those are the things you could kind of look for to help you decide, you know, what is that group that's there on the top as well. So why don't you take a second here? Why don't we draw this guy into the alpha cyclic structure? So take a second or two, see what you come up with. Okay, so let's take a look at it. First off, we can number our carbons. Remember, always starting at the most oxidized group, which is up there, that ketone group or that aldehyde group in this case. 1, 2, 3, 4, 5, and 6. Again, in the 6th situation here, it is going to be really that last carbon, or carbon number 5. In this case, it is going to go all the way there to the top to find that carbon oxygen double bond. And again, if we just sort of highlight what we got going on, we got 1, 2, 3, 4, and 5 carbons. So that basically tells us the ring we should draw is a 5-carbon ring. Remember, it looks like cyclohexane, but it is missing a carbon because the oxygen gets incorporated in there. As we could also see, like normal, our number 6 guy will end up above the ring. That then gives us our foundation to numbers 6, 5, 4, 3, 2, 1 going counterclockwise. Now, again, I'm not going to redraw it, but if we just drop this guy on its side, as we talked about before, everybody on the right will go down, everybody on the left will go up. So starting at carbon number 4, we see the OH is on the left, which means it should end up. Carbon number 3, we also see the OH there is on the left, which means when it drops to its side, it should also end up upwards. And carbon number 2 there on the right, which means when you drop it on its side, it should end up down. As we also talked about, on the other side of these lines are hydrogens, not usually drawn, so it doesn't get so cluttered. Number 1 is going to be determined by this, which is alpha. Alpha should mean down, so that last OH group there going to end up down. Any questions on that there? Again, if you have less than sort of 6 carbons and you want to do this, basically it's usually your last sort of chirocarbon from the bottom is the one that will come in and close up the ring. Any questions on that there? Hopefully they agree with us. Looks like they do. That's good. All right. So continuing on, we're going to talk about some of the chemical properties of monosaccharides. A lot of monosaccharides are pretty much what are referred to as reducing sugars. And reducing sugars basically means that when you have a monosaccharide with a carbonyl group, which is pretty much everybody, that will oxidize to a carboxylic acid, it is what is referred to as a reducing sugar. So the thing that gets oxidized is what is known as a reducing agent, which is why it's referred to as a reducing sugar. When they undergo reactions with Benedict's reagents, like we talked about when we were doing organic chemistry, and basically this reaction here, where we go from an aldehyde to a carboxylic acid, again, inserting basically the oxygen there, it will basically change color, go from like blue to like that orangey brown color. It includes pretty much all your monosaccharides, your glucose, your galactose, and your fructose do have the ability basically to do this. So here's an example of it. If we take glucose here and we treat it with Benedict's reagents, we're going to see our oxidation occur here, and pretty much identical to the aldehyde to carboxylic acid oxidation we talked about. The result of that, as you can see here, it kind of goes from a bluish color, the copper solution, to I'll call it an orangey reddish color. Again, much like in organic chemistry, if you look really at the bottom part here, you know, nothing else changes. Everything remains exactly the same. So as we talked about with organic chemistry, you know, there's pretty much just like one spot on the molecule that changes. And that's basically, in this case, this particular spot here. Now, the reduction of monosaccharides involves a carbonyl group, and it involves, it will produce what is sometimes referred to as a sugar alcohol. So if you go through the reduction process, you get basically a sugar alcohol, and alcohol, like in organic chemistry, is the OH group. So obviously we have a lot of OH groups here, and they're sometimes referred to as sugar alcohols because the base of it is basically a sugar molecule, a carbohydrate molecule, so sometimes referred to as sugar alcohols. Where you don't have to obviously do any of the namings of the sugar alcohols or anything like that, but like what you get in here, sorbitol is basically this as a result of a reduction of the monosaccharide. Remember, reduction means one of two things: either you have lost oxygen or you have gained hydrogen. And if you think about if you go backwards and do a reduction, again, basically you're going to add a hydrogen there, and you're going to add a hydrogen there. And what you end up with, kind of like an organic chemistry there, is your alcohol, your kind of primary alcohol sort of deal. And that's, again, what we're talking about here, kind of taking the aldose carbohydrate and putting hydrogen back on and making really like the alcohol, kind of the exact same thing as we did there in organic chemistry. So if we look at something like this, we want to write the oxidation and reduction part. So oxidation part, just like in organic chemistry, just going to insert an oxygen there to make our carboxylic acid group. And pretty much everybody else down the road here, let's see, 2, 3, 4, 5, will be exactly the same. So we got a couple of H's there, and an OH, and an OH, H, OH, and OH. And obviously, if we went the other way, which would be our reduction, I'll put an R for reduction. Here we're going to basically add H2. So just as I did a second ago, we're going to put an H there, and we're going to pretty much insert our H there. And what that's going to give us is CH2OH. So the top guy basically becomes this. And then again, everything else remains the same: 2, 3, 4, 5. Nothing else changes. Any questions on that there? So hopefully you can see they're pretty much the exact sort of reactions that we got. And as you can see, again, really the only thing in the box that's in, I said again, the only thing that changes is what's in the box there. Again, everything else remains the same. So these are some monosaccharides we've been talking about. We talked a little bit the other day about disaccharides, and disaccharides are basically when we put two monosaccharides together, and we get some good stuff like some milk, lactose, and some cheese and all that good stuff. We basically put our monosaccharides together by simply removing water, basically. So the removal of water is essentially how we sort of join these guys together. Thing you do need to know is this. So you do need to know that, and we're going to look at each of these individually here in just a second, but you do need to know that the disaccharide maltose is made up of two glucose molecules. You need to know that lactose is made up of a galactose and a glucose. And lastly, you need to know that sucrose is made up of fructose and glucose. So this slide's a good one. You do need to know those things, that the disaccharides here, and basically the two monosaccharides that basically make them up. And again, basically we're going to be taking each monosaccharide and removing water. And again, that's going to tie those guys together. So let's take a look first off at maltose and sort of what it is looks like and how it's really connected. So maltose is a disaccharide known as malt sugar. As we just saw on the previous slide, it is composed of basically two glucose molecules that are basically obtained through the hydrolysis of starch, which basically means we're going to take out water. So basically you're going to have I'll just draw part of the molecule here. You're going to have a glucose molecule here that's got a OH group. You're going to have another glucose molecule here that will also have really an OH group. And basically what you're going to do is kind of take out water. So we're going to take out, let's do it this way. I guess I could drew it better. We'll go that way. I'm gonna take out water basically, and these guys are going to join together. So water is going to come out. And the connection that we're going to get between the two different glucose molecules is what is referred to as a alpha 1,4 glycosidic bond. So let me kind of fill in the rest of this here. Just kind of draw the ring. Very badly drawn ring, but we'll do our best here. There we go. So up above here, CH2OH, we got our CH2OH. So you might be wondering where these guys kind of come from. Well, the alpha is because originally the OH group here at carbon number 1 was an alpha. So this is actually carbon number 1 of this glucose molecule. And that's why it's called alpha. 1,4 refers to the two carbons that are involved in the bond. So that is carbon 6. That is carbon 5, 4, 3, 2, and 1. So that is the 1 of the 1,4. If we go to the other glucose molecule, that is carbon 6. That is carbon 5. That is carbon 4. And that is where the 4 comes from. So carbon number 1, which had an OH group going down in the alpha position. And that's why it's called alpha 1, because that is the connection of the carbon in one glucose molecule to the carbon number 4 in the other. So you do need to be able to sort of recognize this bond as an alpha 1,4 glycosidic bond. How do you recognize it? Honestly, the alpha 1,4 looks just like this. Kind of comes down, if you will, comes down to an O and then up, kind of makes this sort of connection. And we'll see a different type of bond here in just a second, but this is the typical way it kind of looks when you got an alpha 1,4 glycosidic bond. It kind of comes down to the oxygen and then back up to the other glucose molecule. This is the guy that's used in cereal, candles, brewing. It does found in the alpha and beta form. And what that means is, for example, it would be this guy here, either up for beta or down for alpha, the OH group on carbon number 1 of this guy, the second glucose molecule. So again, either up or down on that. So let's take a look at a prettier picture than what I kind of scribbled together there. So here we have our two glucose molecules. Remember, carbon number 1 is where we have our alpha. And this is where the connection is going to be, again, the removal of water here. Going to create, as I showed you on the other slide, this sort of downward connection with the oxygen in the middle, which is our alpha 1,4, again, because it is carbon number 1 in this glucose, and it is carbon number 4 over here in that glucose. This is the alpha anomer of maltose. It is alpha because of carbon number 1 on this guy. We see the OH group is down. Question on that there. So again, always that alpha 1,4 has sort of that look to the bond when it comes together. I think of it as sort of going down, if you will. Now, lactose is another disaccharide. Lactose, again, you do need to know, obviously, maltose, the two that make it up, which are two glucose molecules. Lactose, you need to know that it is made up of a galactose and a glucose, basically. So basically made up of a galactose and a glucose molecule. And it's made up of a beta D-galactose. And that is because when we look at galactose, which is right here, we go to carbon number 1, we see the OH group is up, hence the beta. And the connection that we see here is what is referred to as the beta 1,4 glycosidic bond. And for the same reason as carbon number 1 there, over here, that is 6, 5, and 4. So the connection here is going to happen. We'll kind of circle here. We're going to take out the water there. And the connection that we get is different looking than the alpha because beta is kind of up. You actually get this upward sort of bond when you do the beta 1,4 bond here. Again, that looks very much different than what we just saw a second ago with the alpha 1,4. So again, that sort of difference there where you look at it, if it's kind of going down with the oxygen, probably an alpha. If it's kind of going upwards in the oxygen, is going to be a beta here. Obviously, water coming out as to put them together. This is the alpha lactose. Again, it's alpha lactose. By the way, this entire thing over here is lactose. Basically, again, made up of galactose, which is this guy, and our glucose, which is this guy. Again, it's the alpha because when we look at number 1 carbon here, the OH group, again, is down. Now, sometimes people have trouble with lactose because they have a hard time breaking this bond and get lactose intolerant because you really have a hard time processing sort of that bond and being able to break that bond sort of correctly. Any questions on that? So again, you need to know lactose is made up of galactose and glucose, and it's held together by the beta 1,4 glycosidic bond. Any questions on that there? Now, sucrose, which is table sugar, it is obtained from sugarcane and sugar beet. It consists of glucose and fructose together, and it has a different connection that occurs in this case. And a different connection is it makes what is referred to as a alpha beta 1,2 glycosidic bond. And that's because the connection here is in 2 different places. It is made up of alpha D-glucose. And again, I'm just going to draw the carbon number 1 for glucose. And alpha would mean it has the OH coming down. Again, the rest of glucose would be there to the right or left. Beta D fructose. Remember, fructose is this guy that has this sort of thing. And beta would mean that the OH is coming up, and we would have the carbon, which is outside the ring, coming down. And this would be carbon number 2 on the ring. So when these guys come together to remove water, it is between the 1 carbon, which is alpha, hence the alpha and 1 in the bond, that's coming together with the number 2 carbon of fructose, which is beta, and hence the beta and 2 part of the bond. This gives you a connection on kind of the right-hand side of both of these molecules, as opposed to like a 1 to 4 type of bond. Here we have a 1 to 2 bond. So this is what is known as a alpha beta 1,2 glycosidic bond. Again, a little bit different than the alpha 1,4, which is again a connection between 1 and 4. The beta 1,4, which kind of goes up, also a connection between 1 and 4. And here we have basically alpha beta 1,2, where the connection kind of goes kind of straight down, carbon number 1 and carbon number 2. I guess 2 down here would be a better place to put it. where it comes in. Any questions on that there? So just like the other ones for sucrose, you do need to know it is made up of a glucose and a fructose as the two monosaccharides. And you do need to know the type of glycosidic bond that it has, which in this case is alpha beta 1 2. So maltose, alpha 1 4 glycosidic bond made up of two glucoses. Lactose made up of a galactose and a glucose held together by a 1 4 bond, beta 1 4. And here are sucrose, which is made up of glucose and fructose, alpha beta 1 2 bond. Any questions on that there? As I mentioned, basically to make these disaccharides, which again, this big thing here is the disaccharide for sugar, basically, or sucrose. We basically remove water. So we take water out to make the disaccharide, which obviously means that if we wanted to break apart a disaccharide, we basically would put water back in and go through a hydrolysis process, which is basically means water. So if we look at this particular guy here, which is the one we were just looking at, which is sucrose, if I want to break this guy apart, I'm gonna basically throw some water back in, and we're going to separate out here. And again, obviously to fix this guy, you need a hydrogen. To fix this guy, you need an oxygen, a hydrogen, which again is water. And we get back our monosaccharides like we had it. So to put our disaccharides together, take out water. To break apart our disaccharides back into monosaccharides, we will add water, basically, to do that. Any questions on that there? So you do need to be able to kind of recognize the glycosidic bonds and sort of identify them as alpha 1 4 or beta 1 4 and so forth. Any questions on that there? So sugars and artificial sweeteners, they do different in sort of sweetness. And this chart sort of compares it, regular monosaccharides, our disaccharides, as you can see, artificial sweeteners like saccharin and aspartame, super sweeter than our normal sugars, which is why we only need a little bit of it when we do that. Also why, if you took like a Diet Coke, I think we might have talked about at the beginning of the semester, in like a Diet Coke can versus a regular Coke, this guy would sink in water. This guy floats in water, again, because Diet Coke has sweeteners in it, artificial sweeteners, which means not put as much sugar. This guy's got a lot of sugar, so it makes it more dense than, say, the Diet Coke. All right, so take a second here and determine for each of these disaccharides, what are the correct monosaccharides that are part of it? Glucose molecule. And remember, this is the one that is held together by the removal of water, and it makes our beta 1 4 glycosidic bond. Again, the one that kind of looks like it is going upwards there. Maltose was the first one that we looked at, which is basically made up of, we'll circle it twice, a couple of glucose molecules. So it's made up of a couple of glucose molecules. And remember that the connection that we see here with maltose is the alpha 1 4 connection. Again, the one that kind of looks like it's going downward. Again, really between carbon number 1 of 1 glucose and carbon number 4. And obviously here, this is carbon 1 and carbon 4 in terms of the connection. Lastly, sucrose, which we were just looking at, is glucose and fructose. And this is the one that has the kind of straight down connection. It looks like this, and that has both of them. It is the alpha from the glucose, the beta from the galactose, and it's going to be alpha beta 1 2 connection, again, carbon number 1 there of our glucose, and carbon number 2 there of our fructose. Any questions on that there? So these are disaccharides. So as I mentioned before, you need to know each of those disaccharides, the connection obviously between them, how they're put together, and obviously the glycosidic bonds that are there, and the 2 monosaccharides obviously that make them up. Now let's talk about polysaccharides. Polysaccharides are pretty much just long polymers of D-glucose guys together. Polymers are just really long chains, and I'll just draw the glucoses as circles. So basically, it is just a glucose molecule attached to glucose, attached to glucose, attached to glucose, basically taking out water in each of the connections, and it runs for a long time. They include things like amylose and amlopectin, starches that are really made of alpha D glucose. Also include things like glycogen, which is sort of where we store our energy, and include things like cellulose, which are plants and wood that are made out of them. So again, it really is just a bunch of these guys together, taking out water basically from the next guy, taking out that water and making that connection like we saw earlier. So let's take a look at a couple of these guys here and sort of talk about some of the differences between them. Looks like some baked potato action going on here. So we have some amyloice and amlopectin, and they are really just long chains of D-glucoses together where we have taken out water. When we looked at amyloice, it is a straight chain, really no branching occurring here. And it has the bond that we were just talking about. That is our alpha 1,4 glycosidic bond. As you can see in between each of these guys, kind of the downward move there. Again, meaning the same thing, carbon number 1 of the first glucose, carbon number 4 of the second glucose, where that connection is basically occurring. Now, amlopectin also a bunch of glucoses together in a straight chain. Also, as you can see, has the same bond, that alpha 1,6, alpha 1,4, I spit it out right, alpha 1,4 glycosidic bond. The difference between these two is in amylopectin, there's actually branching that occurs. And branching means kind of like what it does in organic chemistry. Every so often, you got a straight run, and then like a branch on a tree, you got something shooting up in a different direction. And that's what we see here. At this point with this glucose, we got this downward connection that actually occurs here. And that is an alpha 1,6 glycosidic bond in a branching situation. And again, the reason it is alpha 1,6 is if I draw just part of the glucose molecule here, again, 6, 5, 4, 3, 2, 1, OH in the alpha position. Below it, I probably should draw a little bit better than that there. Move it over. So below it, we actually have carbon number 6 in the next glucose. Creatively drawn glucose, and that's carbon number 6. So here we're going to take out our water, H2. I'll do an O this way. That's a very bad circling there. So we're going to take out our water, and then we do get that connection that actually happens right here between carbon number 1 and this glucose and carbon number 6 really over here in this guy as well. So that's why it's referred to as alpha 1,6 glycosidic bond. So amylopectin is a little bit more branched. It has actually 2 connections that occur. Again, alpha 1,4, like kind of the amyloids, and alpha 1,6 connection happening. You can see that in terms of the sort of starch, if you will, Amylopectin occurs 80% of the time. Amyloice occurs kind of 20% of the time in a starch such as this. So you got a lot of the straight chain glucose coming out, but you got a lot of the branches happening here with the amylopectin. So amyloids, looking at these guys a little bit closer, is a continuous unbranched chain of alpha 1,4 glycosidic bonds that basically just straight through, as we saw there in that picture, and we see here, straight through glucose to glucose with our, again, alpha 1,4 bond happening there. Amylopectin, again, is a more branched sort of version of it, with our branching point happening between a 1 and a 6 sort of connection, alpha, but has the same kind of straight chain, and it picks back up again as alpha 1,4 at these points as it continues on. Just sort of those branch points have that alpha 1,6 branching that occurs. Any questions on that there? Now, another sort of form of this is glycogen, which is basically when we take sugar in, we kind of store it in our muscles as this, so we could later break it back down through a process known as gluconeogenesis. Glycogen is a polysaccharide that stores alpha D glucose. It is similar to amylopectin, so it's got the same sort of connections there. It's got that alpha 1,4, also the alpha 1,6 connection, except that it has a lot more branch points happening. So it's much more branched out, a lot more branching happening in glycogen than it does in amylopectin, but very similar in sort of structure. Cellulose, on the other hand, is a polysaccharide of basically glucose units that are unbranched. The difference is we got a beta 1,4 glycosidic bond. So again, when we look at this bond, as we talked about earlier, you can kind of see it going in that upwards direction. And again, that upwards direction is a pretty good key that you're dealing with beta here. Just like beta means up, right? So you kind of see that connection going that way. That's a good hint. Just like alpha, right, means down. So when you kind of see the connection going this way, you know, that's a good way to remember it. We cannot digest it, which I guess is good because we cannot break that beta 1,4 glycosidic bond. So don't eat any of the cellulose, obviously. All right, so let's take a look at each of these here. So in this case, we want to identify the polysaccharides and the types of bonds that are happening. This is the one we just saw. That is our beta 1,4 in our cellulose. And that, again, bond looking like that. Here we have both of them. We have amyloids, which is, oops, the wrong spot. Amyloids, which is our alpha 1,4 connection. Again, looking like that. That is the unbranched, straight across, guys. Then obviously we have our amylopectin, which also has the alpha 1,4 connection. And also, again, is branched at that point where we get that kind of straight down move from 1 to 6 in terms of the connection. And that would be our alpha 1,6 connection here. Any questions on that there? And then obviously, this is our glycogen that we just talked about, which is pretty much the same connections, alpha 1,6 and alpha 1,4, but much higher branching occurring. Any questions on these polysaccharides? Okay, so that does wrap up carbohydrates, actually. me one sec. So this week's a little bit later. All right, so let's talk a little bit about lipids. Lipids are biomolecules. They contain basically two kind of things. They contain either a fatty acid or a steroid nucleus, which we're going to look at what both of those are as well. They are soluble in organic solvents, but not in water. And that's because really a fatty acid is nothing more, as we'll see, than a long chain of carbons and hydrogens, which is definitely non-polar. And obviously water, which is polar, means that they are not going to mix well, as one would want to be using dispersion forces. One would obviously want to be using something like hydrogen bonding. They're named for the word lipose, which means fat. You could extract them from cells, obviously, using some type of organic solvents. The lipids contain fatty acids that are one of these sort of classifications. And in this chapter, we'll talk about all these guys here a little bit. Waxes, fats and oils, which are sometimes referred to as triacylglycerols, or TAG for tag, glycerol phospholipids, prostaglandins, and again, we'll talk a little about steroids at the end of this chapter. They don't contain any fatty acids. This is a nice little sort of slide, and I think you should have a similar one in your book. But ultimately, you will need to know, kind of the makeup of what fatty acids look like. And again, we're going to go into each of these individually here. What makes up triacylglycerols? What are the parts, which are nicely listed here? Glycerol phospholipids, sphingolipids, and glycosphingolipids, and obviously the steroid nucleus. So again, each of these will go into a little bit of detail in this chapter, but ultimately that's one thing that you do need to kind of know for the final is sort of what makes up each of these different types of lipids. So let's start with the fatty acid and sort of what the fatty acid is. Fatty acids are, like I mentioned before, pretty much long chains of really carbons and hydrogens. So, for the most part, if we kind of do line structure, they're very long chains of just carbons and hydrogens. Again, just like this, each of these are carbons and hydrogens. And really at sort of one end, they do have a carboxylic acid, which is, again, the same group that we see in organic chemistry. So here's our carboxylic acid part. And really, it has kind of two parts. It has this part here, which can be polar, but because it's really long, this part, I didn't draw obviously 12 to 18 of them, I don't think, but obviously it can continue on. That's basically just carbons and hydrogens. This is really a non-polar part. So one thing that we sort of talked about in terms of, say, solubility in water, when we're talking about organic substances, is obviously solubility in water starts to decrease, even if you have a spot like here. As we know, this is a very polar type of functional group, right? That guy is negative and positive. This guy is positive and negative, and it can interact well with water. The problem is this really long non-polar part really gets in the way, kind of hinders it, and it causes it to be really insoluble in water. The fatty acid part can be saturated or unsaturated, and that meaning is also the same thing that we talked about in organic chemistry. Saturated basically means all single bonds. We have the maximum amount of hydrogens, if you remember. Unsaturated, on the other hand, means you got at least one double bond. The result of that is you got one double bond. That means you do not have the maximum number of hydrogens that you could have. So we could have saturated fatty acids and unsaturated fatty acids. Again, much like in organic chemistry, unsaturated fatty acids would have a double bond, at least one, maybe multiples. Saturated would have no double bonds. And really the presence of those double bonds, or maybe the lack of double bonds, also gives some of these guys different types of properties. Kind of like in organic chemistry as well, we can use a bunch of different formulas. Remember that, COOH is sort of a shorthand that's used in formulas to represent the carboxylic acid group. We could use line structure, again, just like in organic chemistry. These are all carbons, and obviously hydrogens are attached there. I won't draw them all. This is like condensed formula. This is sort of condensed formula, if you will. Again, remember that if you see sort of a parentheses and a number on the bottom there, that basically means that there are 6 of those CH2 units connected in a row, in addition to what else is there, in addition to obviously our carboxylic acid in this case, and we got our CH3. And that's really important, especially if it's written like this, which sometimes it commonly is. One thing that you might need to do is actually count up how many carbons there are. So you want to keep that in mind as you go through. That would be 1 carbon, that would be 2 carbons. And now there's actually 6 of these units, which means there's 6 carbons. So this guy would have 8 carbons in this case because of that. So sometimes people will miscount it because of the sort of parentheses. Any questions on that there? Now, saturated fatty acids, looks like steak, sounds good. Saturated fatty acids have basically all carbon-carbon single bonds. And the result of that is with our non-polar part of our fatty acid, which I'll just highlight here. This part here, what we see is they pretty much will sit very nicely with one another. They'll fit together really nicely. The interactions between like the dispersion forces will work really nicely together because they're all single bonded. The result of that is they will interact well with each other. You have really strong interactions, and that results in a higher melting point, and means that most saturated fatty acids are solids at room temperature because of that really nice tight interaction that you could get because of all the single bonds, hence the steak part of the fat there. Again, solid at room temperature because they interact well with one another. So here's a table of some saturated fatty acids. And you can see all these all have single bonds as you go across. And that means that they're all going to really interact well with each other. They're going to fit in with each other. And we do see relatively good and high melting points because of that. And they're typically solids at room temperature. One way that we can sort of describe a fatty acid is by the number of carbons and the number of double bonds. So for example, if we looked at, say, this first one here and we counted it like they did there, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you don't want to forget the guy right here, 10 carbons with no double bonds. This is what is sometimes referred to as a 10 to 0 fatty acid. 10 meaning the number of carbons, 0 meaning the number of double bonds. We look at our 18 here again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and again 18 right there. And it has no double bonds. This is what is referred to sometimes an 18 to 0 fatty acid. So sometimes fatty acids are referred to that by a number and another number. First number, again, is how many carbons there are. Second number is how many double bonds there are. Now, you get these really nice sort of fitting together of these fats when we have all these single bonds happening on the fatty acid chain. That is not the case when double bonds are pretty much introduced to it. When we introduce double bonds to it, we get unsaturated fatty acids, and they typically contain cis double bonds. You can't have trans double bonds. But what you also see here, again, just like in organic chemistry, cis or trans means the same thing as it does in organic chemistry, right? Cis is same side. Trans is, I'll just draw it like this, opposite sides. The result of actually having these double bonds here actually creates these kinks in the hydrocarbon chain. So we don't get that really nice and pretty, perfect as we do with that single bond that allows those guys to fit really nicely together. We end up getting these guys that get all sort of, the long carbon chain gets kinked out. The result of that is when they try to associate with each other, multiple chains, as you can see here, we kind of get a mess, if you will. We get some spaces between the different chains. Again, they're not sitting as well as I just drew there on the other page. When we are saturated, that makes solids. The result of this is we typically get not the greatest interaction, which we end up getting actually lower melting points than we do in saturated fatty acids. And that's why these guys are typically liquids at room temperature. And those are like your oils, your olive oil and things like that are unsaturated fatty acids. Again, the kinking of the chain because of the double bonds, creating the non-polar part not being able to interact well with one another. Any questions on that there? So here's a table of some unsaturated fatty acids, and we could do the same thing. If we count up all of our carbons here, I won't do it here, but we go all the way across. We have 16 carbons and one double bond. So this is a 16-to-1 fatty acid because of the double bond. This guy has 18 carbons, has one double bond. That is an 18-to-1 fatty acid. Down here, we actually have this guy here, which actually has 1 and 2 double bonds. Also has 18 carbons. That would be an 18-to-2 fatty acid, and so forth here on the bottom. Getting old, but it looks like 4. That'd be a 20-to-4. The result of this is all these double bonds not going to allow those guys to sit nicely to each other, going to have lower melting points, which is what we see here. In addition, look at this guy here, which has got like 4 double bonds. And that's going to create a lot of places where that chain is going to kink up, which means it's going to have a very terrible time interacting with other chains. The result of that, as you can see, has a super low melting point because of that. So the more double bonds you got going on there, the more kinking you're going to get, the less interaction you're going to get between those carbon and hydrogen chains, and it's going to result in a much lower melting point, even within sort of unsaturated. You can see this guy that has, only 1 has a much higher melting point in comparison to this guy that's got 4 double bonds. Since he only has 1 double bond up there on top, still going to get the kinking, definitely going to have a lower melting point and going to be liquid versus a saturated fatty acid, but actually will have a higher melting point than somebody that has multiple double bonds. And that's what is sometimes referred to as being polyunsaturated. Polyunsaturated means you got multiple double bonds happening. Monounsaturated means mono means 1. You got 1 double bond sort of happening. Any questions on that there? And we see that again in comparison of our saturated, which is here, no double bonds, much higher melting points, more solid at room temperature. As we start to introduce 1 double bond to 2 to 3, we see a dramatic sort of, as we saw there, decrease in the melting point. Again, the more double bonds, the more kinking, and that would be the one that we would expect to have the lower melting point. So if we take second here, for each of these, we got one with saturated 18 carbons, 1 double bond and 18 carbons, and 2 double bonds, 18 carbons. And we have melting points of -17, 13, and 69. So take a second and think about which melting point should go with which structure there. Okay, let's take a look and see if we could do a little bit of reasoning as to where we could place these guys. Well, first off, this is 18 carbons and saturated, which basically means it's an 18-0 fatty acid, 18 carbons, no double bonds. This guy is an 18-1 fatty acid, which means 18 carbons, one double bond. This guy would be an 18-2, 18 carbons, two double bonds. Remember, something with no double bonds that is saturated is going to be a solid at room temperature and have the highest melting point. So we would assign the higher number there to our saturated guy. Remember that the more double bonds you put on that fatty acid chain, the more kinking that's going to occur. And that's going to mean less interaction between those chains. And that's going to result in a much lower melting point. So since this is the lowest of them all, we would assume that it would end up over here with our multiple double bonds. And that obviously leaves our guy in the middle here to our guy with one double bond. Any questions on how we came to that conclusion? So talk a little bit about prostaglandins. Prostaglandins have basically 20 carbon atoms in their fatty acid chain. They have an OH on carbon 11 and 15, and they have a trans double bond there at carbon number 13 that's occurring. So carbon number 13 over here, we got the trans double bond. What are prostaglandins? Well, they are produced in sort of injury. So we do kind of produce these guys during sort of injury to help us with pain sort of management, if you will. So hammering your thumb there, not a good thing. That's going to create some pain. And typically what that would do is we would produce some prostaglandins, which basically gives us pain, fever, and inflammation. We do take some type of drugs there to sort of block that prostaglandin formation and thus hopefully alleviate some of your pain and fever and such. So they are basically formed in a sort of natural process as a result to pain and injury in our tissues. And obviously when we take something maybe like a Tylenol or something like that, it helps it sort of block further formation of that and helps us prevent hopefully more pain. Another sort of classification for fatty acids is omega-6 and omega-3 fatty acids. And omega-6 and omega-3 fatty acids are found in a couple different places. Fatty acids and vegetable oils are mostly omega-6. So what that actually means is the first double bond actually occurs at carbon number 6 is what that means. Now, different is how we count carbon number 6. Now, most of the time and everything that we've done, you know, we kind of would think we go to this functional group here and count that at carbon number 1. Actually, when we're doing omega-3 or omega-6 sort of counting, we actually start counting on the opposite end. So this is linoleic acid. This would be carbon number 1. There are 4 carbons here, which gives us basically 4 more. That's 5, which means at carbon number 6 right there is where we see our first double bond occur. So counting omega-6, actually we count away from the functional group, which is odd, but that's how we sort of count it. And again, omega-6 obviously meaning that that first one happens there at number 6. Fish oils have omega-3, and that also we would count opposite of that, again, starting on the opposite side. And this would be carbon number 1, this would be carbon number 2, and carbon number 3 here, where we see our first sort of double bond occurring. Omega-3, omega-6 sort of fatty acids have some health benefits that people sometimes want to take. And again, as you can see, fish oil sometimes is where we get some of those guys from. Here's a bunch of omega-6 and omega-3 fatty acids. And again, you can see sort of opposite of our normal thought process is actually counting opposite of our sort of carbonyl group. So here we see what we just saw there, number 6. We see number 3, 1, 2, 3 here, 1, 2, 3, where we see our double bond first occurring. Any questions on that there? So you do need to know sort of the counting for omega-3 and omega-6, how to count it and how to find it. Again, kind of the one and only thing that we kind of go opposite of the functional group there. So if we wanted to draw a fatty acid with 10 carbon atoms that's saturated, you know, if you wanted to, just do a little line structure, lose track of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We should have a carboxylic acid there. Mono unsaturated omega-3, we would have our same sort of deal. 1, 2, 3, 4, 5, 6, 7, 8, 9. And mono unsaturated means one double bond. Omega-3 would be starting to count on this side, 1, 2, and 3. Again, we would lay up a double bond right there at number 3. Obviously, this would be more line structure. If you did it, monounsaturated omega-6 would be the same thing, except obviously we would go in 6 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. And obviously 1, 2, 3, 4, 5, 6 would be our double bond happening. These are line structures. Here is the condensed structure. And again, we see what we just talked about. No double bonds here in our saturated. Double bond at carbon 1, 2, and 3. And double bond at 1, 2, 3, 4, 5, and 6, basically occurring. Any question on those there? Then let's talk a little bit about waxes, fats, and oils. So waxes are esters of a saturated fatty acid and a long chain alcohol. So what does that mean? If you remember, fatty acid basically has the carboxylic acid group at the end, fatty acid. And long chain alcohol just basically means it's got a lot of carbons, but basically alcohol. We got the OH group. And as you can probably imagine, if you take out water between those two, water goes out. You get your ester bond, which if you remember, looks like this, right? Without the OH group there, again, we get this carbon-oxygen double bond with the oxygen, and that's what we see here. There is our ester bond going towards the double bonded oxygen is our carboxylic acid, our fatty acid. Going towards the single bonded oxygen, that's our long chain alcohol. That's basically happening. Again, you can see that same ester bond basically occurring on each of those things for different types of waxes, honeycomb, waxes for cars and so forth, carnauba wax, and beeswax. Now, let's talk a little bit about triacylglycerols. Triacylglycerols are sometimes referred to as TAG, or used to be, for triacylglycerols. They're also called triacylglycerols. They are esters of glycerol, and we'll see the structure of glycerol here in a second. They are produced by that esterification reaction. And basically, the esterification reaction is basically how we just made an ester there on the previous page. Again, it's the same esterification reaction that we saw in organic chemistry, and I just drew on the other page, which is take out the water, squish everybody together, and we form again our ester bond that is here. They're formed when the hydroxyl groups of glycerol react with the carboxylic acid groups of the fatty acid. So if we take a look at this, this is glycerol here. So this guy is glycerol. You should be familiar with glycerol. It's kind of like the alcohol part. It's got the OH groups sort of happening. Now, obviously, this is our fatty acid, which is basically, you know, our long chain guy that we've been talking about with a bunch of carbons obviously coming off of it. So just like before, we're going to basically take water out. That is going to leave us an oxygen. So if you sort of dissect it, you know, this is sort of your, I guess it's actually this way. It's probably the correcter way of doing it. That is your glycerol unit there. And then obviously on the other side here is your fatty acid to make a triacylglycerol. So one thing that you do need to know is a triacylglycerol is made up of a glycerol unit, which is this guy on the left, and 3 fatty acids. So triacylglycerol made up of glycerol and 3 fatty acids, 1 for each of these OHs. And the bond that holds them together is, again, that ester bond, that exact same bond that we use there in organic chemistry. So we take a look at sort of the formation of this. There's our glycerol unit. There's our fatty acid. Again, out goes water. How many waters? We lose 3 waters, 1 at each of the OH groups there. And again, basically just squish everybody together. And we get our triacylglycerol that's down here. Again, you can see your ester bond that is happening. So triacylglycerol, glycerol unit, 3 fatty acids comes together to make a triacylglycerol. Again, each held together by obviously an ester bond. Any questions on that there? Now, olive oil is an example of that. Here we see, again, kind of our glycerol unit. And again, our fatty acid. And we also see some double bond action happening. So as we talked about earlier, because of those double bonds, these chains are not going to sit really nicely with one another. And basically that means, as we can see there, our good friend olive oil is a liquid at room temperature because of that. Again, it's really because of these chains here and those double bonds that are there. That's not going to allow them to really associate really well with one another. And we do get obviously something more of a lower melting point and something that is a liquid at room temperature. Not important for us to name any of the fatty acid names or anything like that. But again, if we just look at this, if we come here to our left, that is our glycerol unit. And again, our fatty acids are going this way, basically. And again, we do have some double bonds happening there. That's going to not allow it to sit really well. And we would expect sort of a lower melting point there. So obviously triacylglycerols, that is a fat, is a solid at room temperature. And that's typically what we see that's prevalent in meats, milk, butter, and cheese. Those would have on the fatty acid part of that triacylglycerol pretty much no double bonds. So they would be saturated. So again, when that glycerol unit is attached there, the fatty acid part is going to be pretty much all saturated, badly drawn, but all saturated, which means these guys are going to sit pretty close to one another, have good interaction. And again, that's why we're going to see more of a solid at room temperature. Our triacylglycerol there, like we just saw there with olive oil, with the introduction of those double bonds, going to allow those things not to sit really well to each other and be more of a liquid at room temperature, like we saw there, obviously with our olive oil, again, due to the kinking that's going to occur, as we see here. And as we talked about earlier, it was just straight fatty acids as well. There's a better picture of it. Again, all that kinking, allowing it to be a liquid at room temperature. All right, so I think what I'll do is we'll lay it up there. Again, at least we got into a little bit of this chapter in person. Again, you are responsible for this chapter and 16, which again, there has been a recording up there for a while now, so make sure you do watch it. As I mentioned, you're responsible for whatever's in those recordings. Again, it may not be everything that's in these last 2 chapters, but you are definitely responsible for what's in that recorded lecture, some of which we just talked about here today. Obviously, the final, as we've talked about, is going to be 1 week from today, and it should start at 4:45. So again, as I sent out an announcement, I think the other day, it does start a little bit earlier. So make sure, again, you adjust your schedule so you're able to sit down, log in, and take the final. It will be of a similar format to the exams we've taken before. It will obviously have a multiple choice part, I believe. It'll have a written part. And like the exams before, you will need to upload some work for some questions. They will be like normal, clearly labeled on each question as to whether or not you need to upload work or not. When you do upload work, especially for the final, do make sure, obviously, you do have to show all the work obviously associated with it, but just make sure everything is properly labeled in terms of what question it goes to and stuff like that, so I don't have to try to figure out any of that stuff here on the final. And obviously there'll be a multiple choice part where you don't have to show any work, just hopefully pick the right answer. And clearly on the written part, there'll probably be some questions like that too that you don't need to show any work for. The final exam will cover every chapter that we covered, including, again, these last 3. So that's basically 1 through 16. I think the only chapter we didn't do was chapter 5. I think that's maybe nuclear chemistry. So we did skip that chapter. So obviously that will not be on there. Anything that you were provided for previous exams, you will once again be provided for the final, obviously, if you need it. That includes obviously a periodic table, some conversions, constants, those type of values, formulas and stuff like that that you were responsible to know, for previous exams, you're still responsible to know. I will say the test probably is fairly, I won't say perfectly spread out, but it probably definitely will cover the highlights of the entire semester. I'm not going to try to focus on maybe one chapter more than another. There definitely will be questions from these last 4 chapters, I guess. That includes the organic chapter. There are 14, I think, that obviously you haven't seen. So there may seem like there's more questions, and there might be a couple more or so, but my focus is not to do everything on these last chapters and nothing on the previous chapters. So overall, the exam will cover everything from chapter 1 to 16. Obviously, not every single topic can be tested on, otherwise you'll be there all night. But some topics may be combined, but it will be, again, a similar format. You do obviously have to use proctorial and all that stuff like normal. You're expected to start the final around 4:45. Again, it will have a time limit like our normal exams. Whatever the final exam period is, you get a couple hours or so, I think, probably. But you are expected to start that. If you start too late and it cuts you off, then that's on you. So in addition, I did post up some homework problems from these last 4 chapters, chapter 14, 13, 15, and 16. They are not due for credit, but they're up there in case obviously you want to do some practice of those problems from those chapters for the final. It might be a good idea. But again, you won't be penalized if you don't complete them. They're just posted up there for you to at least have some practice problems for those last few chapters and stuff that we weren't tested on. Any questions on anything?
Hello, Professor.
Yeah.
I actually do have a question regarding the disaccharides.
Yeah.
In the test, would we be asked to draw them or just be able to identify them?
Yeah, so for the most part, you won't be asked to draw pretty much too many things these last few chapters. The drawing may be provided to you, and you need to identify them. Either identify what it is, or for example, I said you need to recognize the structure of glucose or something like that. So the structure might be provided for you. You need to be able to recognize it as glucose, but you don't have to draw it. Or you may have a structure where it kind of shows the connection, like we talked about today, of like alpha 1,4, and be able to recognize that. So there are a couple of things maybe out of chapter 16 that you might need to draw, and I think I go over it in the video, but for the most part, more recognizing the structures, if they're provided to you, would be more what would be happening probably in these last 3 chapters.
Okay, thank you.
You're welcome. Honestly, I'm not sure yet. Still working on the final, so I'm not sure how many questions there are. So it should be doable in the time period for the final exam. Probably a little bit more than a normal exam, but hopefully not super more on top of that. Other questions on anything? Okay. So as I said, I've enjoyed having everybody in the class. I hope you've enjoyed it as well. Hope you learned something along the way. And good luck on our final, and obviously your other finals that you may have. And there is discussion tonight, so if you have discussion, I'll see you guys in about 10 minutes. If you're off the lab, have a good, I was gonna say summer, but it's not summer, is it? Have a good winter break, I guess, afterwards. And otherwise, I will see you, those that have discussion tonight. And obviously you have lab if you have lab. Have a good rest of your evening if you're out, and I'll see everybody in about 10 minutes that has discussion.